Hello, my name is Aisling Roverino, and today I'll be presenting Chemical Engineering Group 1 Sulfur Recovery from Magnesium Sulfate. I'm also joined by Arthur Ramirez, Mac Edinger, and Stephanie Worth. Starting with an introduction, we go through the problem statement. The goal of this project is to regenerate sulfuric acid from a magnesium sulfate mining byproduct. With this problem statement in mind, we then went into process design. Step 1 was to conduct literature review to see what options are out there for possible alternatives for a solution. Step 2 is to do process screening. So based on economics, product quality, social and environmental constraints, we decided what were the best options. Then step 3, we selected a process, sized the equipment, and estimated the costs.
So the significance of our solution was evaluated in terms of the sustainability, where are recycling a waste product into sulfuric acid to reduce the need to purchase new sulfur and produce sulfuric acid on site. Any mining operation where magnesium sulfate is produced as a waste product from sulfuric acid leaching would have an interest in this, and that includes most lithium and copper mines. As a sense of scale, there's about 88 commercial lithium mines globally. So moving on to engineering design. In this project, we incorporated the following major core concepts into our engineering design, where we applied engineering standards to protect public welfare as a demonstration of our understanding of engineering ethics. Within a global context, we found a waste material from mines and was able to find a use for it. And then we incorporated engineering concepts like engineering economics, heat transfer, energy balances, and process design into our solution.
Engineering principles were applied in order for us to meet our process constraints. Firstly, we considered ethics, wherein the public and environmental health are incorporated into the process design. Then we considered research and process flow diagrams, wherein we research similar processes and visualize the solution in a process flow diagram or block diagram. Then we designed our equipment based off process requirements. This involved the use of engineering heuristics and calculations. And finally, we conducted an economic evaluation and further optimization of our process, utilizing pinch technology for efficient energy recovery and reuse across the process.
For our engineering standards, we had to consider how the mine tailings were stored. At the end of this process, we end up with a substantial amount of magnesium oxide that must be stored properly in containment ponds, and groundwater should be controlled in such a way that it doesn't produce any sort of toxic runoff. SO2 emissions are also to be considered and will be monitored to make sure that they do not exceed EPA regulations or allowable limits per year. Moving on to global impact, this design is original and innovative because it is currently not existing in any sort of mining operation as of today. It's very useful. Sulfuric acid is used for leaching in many different products and productions. So to be able to implement this within these processes would be incredibly useful and save a lot of companies a lot of money. There's nothing that is within this process that could not be built today. This could be implemented and built by many design build firms that exist currently today.